Hi, this is the design of a heat pipe.
I'm Chelsea.
I'm Josh.
And I'm Casey. We are the CRH Corporation, and this is for ME 412 Heat Transfer Lab at Michigan State University.
For the design of the heat pipe, we had three factors to consider: working fluid, pipe materials, and pipe geometry. For working fluid, we considered ammonia, water, and acetone, with water being chosen as it has the highest heat load capability, but it required a vacuum within the pipe, which affected the design. The pipe materials, copper was chosen over PVC due to its conducting capabilities. However, the valves remain PVC due to cost and weight factors. The pipe geometry, we decided to move the condenser out of the steam from the beaker. This required two 45-degree elbows, allowing repositioning of the condenser. For fabrication, the heat pipe was primarily made of copper and PVC. Copper to copper joints utilize solder, copper to PVC joints utilize silicone, and all thread utilize Teflon tape. The condenser used a rubber stopper with a barbed brass hose fitting within it. The barbed PVC valve was then attached via steel pipe couplings, and the steel couplings attached to the PVC valve, which attached to the brass barb fitting within the rubber stopper.
So to test it, we added 50 milliliters of water to the condenser end, then shut the bottom valve. This allowed us to pull a vacuum through the rest of the heat pipe, and we brought it down to right around 3 kPa. From there, we closed the top valve and opened up the bottom valve again, so it was all one unit. We disconnected it from the vacuum pump, and then we actually went to testing. To do this, we used two beakers, one as a control, one as the actual experiment, and we rinsed both beakers initially to raise them up to temperature with boiling water. Then we dumped that water and then added 1 liter of rapidly boiling water to each beaker from there. We then placed the heat pipe condenser in one of the beakers with the evaporator just outside of the rim of the beaker and recorded the starting temperature in both beakers and the final temperature in both beakers after 15 minutes. We then compared the results. So we had, starting out in both beakers, temperatures of 190 degrees Fahrenheit, which is roughly 88 degrees Celsius. For the final of the control, we got right around 76 degrees Celsius, and for the beaker with the heat pipe in it, it was a little bit lower at 73 degrees Celsius. You can see our testing setup in the picture.
So in conclusion, our heat pipe was effective. It heated up very quickly, and we knew it was effective because the final temperature of the beaker with the heat pipe in it was less than the final temperature of the control beaker. However, the temperature was only a few degrees lower, so it was only slightly more effective than the actual control. This is probably due to the large difference between temperatures between the water and the ambient air, which causes rapid evaporation in both systems. The overall cost of this project was around $60, so between the three of us it was about $20 each. Most of the materials were bought locally at Home Depot or Ace Hardware. However, some things we did have to buy online via eBay, and that incurred additional shipping charges. Thank you.